In chapter 12, we're going to learn about group homomorphisms. We already learned about group isomorphisms, and isomorphisms were functions from a group to another group that were one-to-one and onto and preserved the group operation. Now, a homomorphism is very similarly defined. A group homomorphism is also a function phi from G to G bar that preserves the operation. It doesn't have to be one-to-one and it doesn't have to be onto, but it does have to preserve the group operation. And so we still have that phi of AB is equal to phi of A times phi of B. Now, a second definition, since our homomorphism doesn't have to be one-to-one, it's possible that there are more elements in G that map to the identity. And the set of elements in G that map to the identity in G bar is called the kernel of our homomorphism phi. So kernel phi is all the elements in G, so all x in G, such that phi of x is equal to the identity in G bar, and I'm going to call that E bar. So just to write it a little bit different, so those are all the things, all the elements in G that map to the identity in G bar. Now, one note, so the kernel of phi consists of elements in G. So it's a subset of G. Even though it's defined via a property that has to do with the identity in G bar, the kernel of phi itself is a subset of G, not of G bar. And so we could draw a little picture. If over here I have a group G, and then over here I have my group G bar. In G bar, somewhere there is the identity, so that's E bar. And then over here, we have different elements that might all map to the identity. And so all those things that map to the identity, that's our kernel. So these things right here is our kernel of phi, and so it lives in G. It's a subset of G. Let's look at an example to illustrate what's going on here. So let's look at homomorphism phi that goes from the real numbers without zeros to the real numbers without zero, and it's defined by phi of x is the absolute value of x. So it's really just the absolute value of x. And we want to show that this indeed is a homomorphism, and we want to find the kernel of this map, of this homomorphism. All right, well, there's only one thing we need to show that this is a homomorphism. We just have to show that it preserves the operation. So we just have to take two elements in our real numbers without zero, r star, and then we're going to look at phi of xy, and we see what that's going to be equal to. So what we want to show is that phi of xy is equal to phi of x, phi of y. All right, so what's the definition of phi of xy? Phi is defined as phi of x, the absolute value of whatever the x is. So phi of xy is the absolute value of xy. But the absolute value of x times y is the absolute value of x times the absolute value of y, and that's exactly the definition of phi of x times phi of y. So that's all. So we have shown that phi is a homomorphism. Okay. Next, we are interested in figuring out what the kernel is. So what is the kernel of phi? Well, by definition, it's all x in r star, the real numbers without 0, so that phi of x, which is the absolute value of x, is equal to the identity in r star, and the identity is 1. Since this is a group under multiplication, the identity is 1. And so you can think about for a while what values, what real numbers in absolute value are equal to 1. Well, there are 2 of them. There's 1 and minus 1. So that is a kernel of this homomorphism phi.